All right, fam, welcome. I am going to give a very crash course here on simulations using the random digits table. So I'm going to try and go through this quickly but not confusingly. Bear with me. First of all, these are the 5 steps that I'm going to follow. Pause the vid and copy it down if you want to. But I'm going to be referring back to like step 1, step 2, step 3. That's what I'm talking about when I'm doing this, okay? And this is my key. So what I'm going to do is I'm going to just kind of explain it. But first you can go ahead and pause the video, read through the prompt. We are selecting a student of the month for 10 months out of the school year. And we have a breakdown, which is very important for our model, step 1, that I'm going to refer to in a second. We have this many seniors, this many juniors, this many sophomores in terms of percentages. And what's weird about this question is that for 3 months in a row, a junior has been selected and all the seniors are pissed, okay? And so what we want to do is we want to decide how likely is it that we get 3 juniors in a row, or the question does say 3 seniors in a row also. There's the or. And so we're actually going to like mock draw numbers out of a hat randomly. We have to assign the numbers to mean something. And we're going to actually see how likely it is to get 3 juniors or 3 seniors in a row if you just randomly choose students, okay? So are the seniors valid with being pissed off that they have 3 juniors in a row as student of the month? We are given a portion of the random digits table. That's how these are going to look. And they're going to tell you where to start and how many trials to do. Okay, so step 1, the first thing I am going to do is I'm going to set up my model. What that means is what numbers are we going to use? And what are they going to stand for? And notice how it says we can avoid having to make 3-digit selections. It's a lot easier to select 2 digits at a time than it is 3. So for example, if we use the numbers 1 to 100, because these are percentages up here, keyword, if we use the numbers 1 to 100, what if the numbers 1 through 48, and I'm putting 0, 1 through 48 because they have to be 2 digits. What if I let those numbers represent seniors? And therefore, if 46% of the numbers, that would be these numbers, represent juniors, then the remaining 6% are going to represent the sophomores. That would be 95, 96, 97, 98, 99, and 00 to represent 100. I guess we haven't used the number 00 yet, and that is how we do not have to use 3-digit numbers. These are going to be sophomores. So step 1, identify the model. That means what numbers are we using and what are they going to represent? Step 2 is what are we going to do for each trial? So if you kind of start looking at our random digits table, the first 2-digit number I see is 68. What does that mean? Okay, so let's look at our legend here, or our key. 68 happens to be a junior. That means the first student that I called for student of the month was a junior. The next number I'm seeing is 41. Okay, great. So 41 represents senior. That means the second student of the month was a senior. And what I'm going to do is I'm going to repeat. The next number is 73. That represents a junior. The next number is 50. That represents a junior. The next number is 13, etc. And I'm going to do all 10 numbers right here. You can see with my highlighting like what they stand for. Okay, so that is step 2. What are you actually doing each trial? We're going to generate 10 numbers. And here's something that's very important. Repeats are allowed. And that's because these represent percentages, not specific students. We actually don't know how many students are taking stats. We only have percentage breakdowns. So repeats are allowed because they do not represent specific people. Pay attention to that when I talk about the second example. I'm going to come back to this and explain that a little bit more. All right, so step 3, once we have our 10 numbers, which are represented right up here, these 10, you can write them out if you want, if it helps you, but remember the first number was 68, the second number was 41, etc. Once we have our 10 numbers, what are we actually looking at? What are we counting? What are we trying to answer? Like, what do we do with our numbers? We are going to say yes or no. Do we have 3 juniors in a row or 3 seniors in a row? I think I said that backwards. 3 seniors in a row or 3 juniors in a row, yes or no? For this first trial right here, I do not have 3 green dots in a row, and I also do not have 3 blue dots in a row. That's why I said no. Okay. Repeat for a large number of trials is step 4. Okay, when I repeat this for a large number of trials, that means I need 10 new numbers. Okay, so 65 was my last student of the month for that first trial. Now let's do it again and see what happens. So my first number is 85, that represents a junior. My next number is 8, that represents a senior. My next number is 95, that represents a, sophomore, congratulations. But look, the next 3 numbers in a row represent juniors. Ding, 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 ding. We have 3 juniors in a row. I am gonna put yes, right here. Yes, I got 3 juniors in a row. They're right there. And you'll notice that I didn't keep highlighting because I already answered the question. But this is my, what did I have? 1, 2, 3, 4, 5, 6. This is my 7th person. This is my 8th person. This is my 9th person. This is my 10th person. So trial number 3 starts here. Person number 82 represents a junior. And you repeat, okay? So you can kind of look through what I've done up here and you can check your answers with what I wrote out. And yes, it does say to do 10 trials. That means we're doing it 10 times. And I only got 3 different no's. All the rest of the time, you can check up here if you want to. I got 3 yeses or 3 juniors in a row, or I got 3 seniors in a row. So the probability of getting 3 of those in a row based on our 10 trials is 7 out of 10. We got 7 yeses out of 10. And how you write your conclusion is step 5. Remember, in stats, the conclusion is probably the most important part. According to our simulation, yes, there are other ways to assign your numbers as juniors, seniors, sophomores. What if we use numbers 0, 1 through 0, 6 first to represent the sophomores? What if we did that? That is also correct. That would have gotten you a different number of trials, okay? What if we had assigned our numbers differently? There are multiple ways to correctly assign your numbers for the record, but according to this simulation, the probability of blah, 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 say something in context about the student of the month, juniors and seniors, is 0.7. Now let's look at the second example. This one I'm not actually going to draw out the numbers, but we're going to set it up. Stats class picnic. We have 18 students. They want to play baseball or softball. It just so happens that 6 of those peeps actually play baseball and softball. What are the chances that they all end up on the same team? Did the teacher stack the deck? Did she rig the team so that all 6 players were on the same team? Let's simulate choosing the 6 baseball or softball players out of the group of 18, okay? So for this model, step 1, what numbers are we going to use and what are they going to stand for? We don't have to use the numbers 1 through 100 here. We only have 18 students. So how about we only use the numbers 1 through 18 and we ignore repeats and any number that's higher than 18 because it's irrelevant to this problem. Let me compare and contrast real quick. Up here we were given percentages. We used the numbers 1 to 100, kind of. We use the numbers 0, 1 to 0, 0. Okay. Down here, we only have 18 people. So let's pretend like we number them 1 through 18 and we are only interested in numbers 1 through 18 and we ignore everything else. Let's talk about the repeats for a second. We're ignoring repeats because these numbers stand for specific people, right? We have 18 students. Everybody has a number. I can't call number 3 twice. Okay, up here I used the repeats. That's because they did not refer to specific people. It was a percentage breakdown. That's a really important difference between when we're using percentages and just letting the numbers represent a percent versus when the numbers represent specific people. We are going to ignore repeats. Anyways, let's let numbers 1 through 6 represent our 6 students who happen to play baseball and softball, and let's let numbers 7 through 18 represent everybody else. Okay, could I have done numbers 1 through 12, the non-players? Yes, I could have. And that also would have been correct, but it would have given us probably different results, and that's okay. Still correct. Step 2, what am I doing? How many numbers do I need? Well, if I'm dividing 18 people onto 2 teams, that means I need 9 numbers. And yeah, they need to be unique because they represent specific people. I cannot have repeats. Okay, I'm going to pick my 9 numbers. Let's pretend up here that I'm using this. 68 is irrelevant, 41 is irrelevant, 73 is irrelevant, 50 is irrelevant. It looks like my first person I'm calling would be person 13, who is a non-baseball player or softball player. Okay, and I would continue looking at my list until I had 9 numbers that were between 1 and 18. And then I would look at them and I would decide, do I have all 6 on the baseball or softball team? Okay, so once I have my 9 numbers, I think in class I wrote hypothetically 9 different numbers on the board in between numbers 1 and 18, and we like circled the ones that happen to be baseball and softball player. So step 3 is yes or no. Do I have all of the numbers 1 through 6 on one team? Or spoiler alert, if you have none of the numbers 1 through 6 on one team, that means they're all on the other team, so that would still be a yes. Okay, and then I would repeat the process 10 times, and then I would write my conclusion. Okay, so that is step 4, and that is step 5. Great. Now let's talk about the last one. So a couple things to get copied down. First of all, waiting time simulation, aka a geometric probability or a geometric simulation. There is a really important keyword that's a difference between this question and others, and that is until. Okay, we want to know how many trials we have to do until we have collected all 4 of these toys. So my daughter Taylor loves McDonald's and she loves Happy Meals, and we spent some time in class talking about which of these toys would you choose to get. But my daughter Taylor wants all 4 of the stupid toys. They happen to be trolls, I think, right now at McDonald's anyways. So I have to keep buying these Jolly Meals, these Happy Meals, until I have all 4 toys. And yes, it's possible to get 2 of these Irish accents in a row. Dang it. But I want all 4 of them. So how many times do I have to buy the meals before I get all 4 of the toys? Okay, so we are going to start at line 101. We're going to do 10 trials, and let's see how this works. Here is the really important thing. This is a geometric simulation. We're doing a geometric prob, and so we don't know how many numbers we need to generate. That is a big difference between number 1, number 2, and number 3. Keep in mind, for example, 1, we were doing 10 months, so we generated 10 numbers, and we looked at like what kind of student got the student of the month. Example number 2, we needed 9 players to be divvied up on the 2 teams to play baseball or softball. Therefore, we generated 9 numbers. Here, we don't know how many numbers we need, but I'm going to start with my model, which is step 1. And how about we only use numbers 1 through 4 for this? Let's do single digits. This is actually going to go really quickly, and that's because we only have 4 toys. And how about we ignore all the other digits and we only focus on numbers 1, 2, 3, and 4? Yes, there are other ways to set up your model. Maybe you could use numbers 1 through 25 to represent 25% of the toys are toy number 1. There are other ways to do it. Okay, I think this might be the easiest one though. Each number 1 through 4 represents one of these toys. I already numbered them up here. So number 1 is the Irish accent, number 2 is the fart machine, etc. Things you never thought you would be saying in stats. For each trial, how many numbers are we going to generate? Okay, well, we don't know. We have to keep generating numbers until we have one of each toy. Okay. And then after each trial, once I generate all my numbers and I end up with a number 1, a number 2, a number 3, a number 4, and probably several repeats of some of those numbers, how many meals did I have to buy? That's the question. How many numbers did I have to generate, which represent how many Happy Meals did I have to buy, until, keyword until, I had all 4. Here I'm going to repeat for my large number of trials, and then here's my conclusion. So let me show you how this one's going to work. So I'm going to start at line 101 like it's telling me to, and the number 1 represents this toy, the number 2 represents this toy. All right, so number 1, very first meal that I bought, I get the Irish accent. Number 9, I ignore. Number 2, the second meal that I bought, I get the fart machine. Great. Okay, the meal 3 that I bought, dang it, I got another fart machine. I did not need 2 fart machines, but now I have 2 fart machines. That's great. Number 3, I now have what is that one? The teeth. I'm going to ignore number 5 or number 9 because there is no toy number 9. I'm going to ignore number 5. I'm going to ignore 0. I got a number 3 again. And then finally, I got the 4th toy. So how many meals did I have to buy? 1, 2, 3, 4, 5, 6. I needed to buy 6 meals in order to get all 4 toys. Now I'm going to repeat. Okay, so where did I leave off? Right here. So now I'm going to this next number. There is no toy 0, there is no toy 5, there is no 7, no 5, no 6. Okay, ding, ding, ding. The first toy that I get is the fart machine. There is no 8, there is no 9. The next toy I get is the Irish accent. The next toy I get is the teeth. There is no 9, there is no 6. And finally, I got the number 4 that I needed, which is the trick or turd. Okay, and so how many meals did I need to buy? 1, 2, 3, 4. Wow, I got all 4 on my first 4 meals. Super, Taylor is very pleased. Now let's try number 3. Where did I leave off? There is no toy 0, there is no toy 9. Here's a 1, here's a 2, there is no 5, here's a 3. I got a 1 again, dang it, I got a 4. Beautiful. How many toys did I need to buy? 1, 2, 3, 4, 5 meals. That's this one. And then you can keep going and you can check your work, but that's the numbers that I'm looking at. So what's interesting, I kind of tried to do different colors here. But you can count, there were 8 meals until I got all of them. And then I had to go for a really long time up here. I was looking for a number 3. There it is. Finally, it was toy number 3, the teeth that I was desperate for. And I had to buy a lot of toys for that 5th trial. I had to buy 12 of them, 12 meals. You can go ahead and double check me on that. Make sure that understands. I'll save these for studying. But after we repeat for a large number of trials, it told us to do 10 trials, then I'm going to average these together. How many meals on average did I have to buy to get all 4 of these stupid toys? It ends up being 6.9, and here is our conclusion, okay? Thanks for watching. Thanks for playing. We are going to do a day next week of more simulation practice, but that is your crash course. Let me know what your questions are. You guys, love you all.